Thank you, Ross, for the introduction. As you said, I started on DVBH about 10 years ago. I did my PhD on that. But after that, I didn't really do that much on broadcasting anymore. As you heard, I work on localization and IoT. But I'm presenting here today on infrastructure cost, power consumption, and radio frequency exposure in TV white spaces, and a comparison with LTE networks. It's the work of my colleague Rodney Martinez Alonso, who is a student that obtained a grant at our university. He's from Cuba, and Ghent University foresees grants for developing countries, developing on the level of ICT infrastructure and connection. Because in Cuba the internet infrastructure is not that great, he obtained this grant, but since he's from Cuba, he couldn't enter the country, so that's why I will be presenting here today. As I said, connectivity is still a challenge in areas with low population density, for instance in Cuba. And as the density of users per square kilometer decreases, the costs to install a network increase drastically. Although Cuba has a relatively high index of human development and high educational level and ICT skills, it is still one of the countries with the lowest connectivity levels. They are at the 135th place in the world ranking, and at home people have only access to internet. Only 6% of the population has access. You see that more than 80% of the municipalities has a population density lower than 200 inhabitants per square kilometer. And it is exactly there where people have the lowest income. People with lowest income have the lowest access to internet there. So this is a region where particularly TV whitespace technology can be interesting as an alternative to traditional internet access via, for instance, LTE. When using the dynamic TV band, the VHF and UHF bands, you have a larger coverage area thanks to the more favorable propagation characteristics at lower frequencies. With the TV whitespace technology, we can better make use of spectrum that is available. It also allows fast deployment, and it has a lower cost per base station, as we will see later on. So the goals of this research were to investigate the trade-off between power consumption, exposure, and infrastructure costs for TV whitespace technology, the IEEE 802.22b standard. Compare a realistic rural and a suburban scenario, and compare that with LTE technology at a frequency of 2.6 gigahertz. So I will first present the scenarios we have investigated and the configuration. Then I will give some link budget parameters that we have used for the design of the wireless network, the models and the metrics that have been used, the optimization algorithm to design the network, and then I will present the results and finally the conclusions. So at the left you see our rural area, which is the area of Boyeros at the outskirts of the Cuban capital Havana. It has less than 200 inhabitants per square kilometer. And it is an area of 169 square kilometers in total. According to numbers that were obtained from Cuban telecom operators, a realistic number for the number of concurrent users there is 135 with an assumed bit rate of 1 megabits per second. The figure on the right then is a more suburban area in Ghent, in Belgium. It's an area of 68 square kilometers, and it has around 1,600 inhabitants per square kilometer. And in this area, there are on average 224 concurrent users, also based on numbers that we have obtained from our telecom operator in Belgium. So which receiver configuration do we assume? So you have the base station, which has a height of 30 meters in the rural environment, 50 meters in the suburban scenario, we assume. And it's a mixture of either line of sight or non-line of sight reception based on shape files we have of the area. And the receiver is assumed to be on the rooftops and is then connected with a wire to the indoor area. And for digital terrestrial television, this is a typical installation. So it's a fixed receiver, as you see. Then the link budget parameters. So both for 802.22b and LTE, the range of the radiated power is assumed similar between 12 and 36 dBm. So depending on the optimization goal, this will be higher or lower. The frequency 600 versus 821, it was 2600, I believe, was used. So I think that's not correct in the slides. The bandwidth for LTE in Ghent we use 10 megahertz, in Cuba 5 megahertz, and for TV white spaces it's 6 and 8 megahertz. Here the number of subcarriers, the number of used subcarriers. For LTE we foresee an interference margin of 2 dB, and for TV white spaces we assume no interference if there's a sufficient number of channels that is available at least. The antenna heights I have discussed. The receiver antenna height is 3 meters. Based on experimental data, we have shadowing and fading margins, which are higher in the suburban case than in the rural case. These margins are for a coverage percentage of 90% and with an availability of 99% of the time. Depending on the modulation scheme that is used, the SNRs vary between, for LTE for instance, between 3 and 22 dB. Noise figure is based on numbers that have been found in literature, are slightly higher for LTE. So the power consumption model we use for LTE, I think in total it was about 350 watts, which is higher than for TV white spaces, where we have at maximal radiated power around 64 watts. This is partly due to, for instance, the use of air conditioning in the LTE transmitter. And as you see, for TV white spaces, the transmitter consumes 6 watts. If the base station is not active, so the EIRP is 0 watts. As the radiated power increases up to the maximum of 36 dBm or 4 watts, the power of the radio unit increases to 28 watts, and the entire base station for that EIRP is assumed to be 64 watts. So that's quite a bit lower than for LTE. The metric we have used for exposure is a rather simple metric. It's the average of the median exposure and the 95 percentile field strength, and the reason for this is because we want to not only have low exposure on average, but also we want to limit the maximal exposure values. Contributions of different base stations are assumed to be uncorrelated and can be combined according to the formula in the bottom of the slide. The cost of a base station, again based on numbers from literature for TV white spaces, we obtain a cost per base station of around $16,000 for LTE. We assume a cost of around $80,000 and that's assuming that part of the base station hardware is already available. The algorithm that we use to design our network actually. So we have a random distribution of users in our area. In the rural area 135, in the suburban area 225. And we generate a set of users 36 times. And this represents a temporal variation or a movement of the user. So the network can be adapted accordingly with the distribution, the spatial distribution of the users. So for each of these simulations, in fact, for each of these user distributions, we look at the fitness value for each of the users that are consecutively added. The optimization function is shown on the right, and it's a translation of the fact that either you want to minimize the global power consumption of your entire network, or either you want to minimize the global exposure of all the users, not only of the users, but of the entire area. So also the people that are not using the network are of course exposed. So it's a global value for the entire area. And if you adjust the weights, W1 or W2, you give more importance to either a low power consumption or a low exposure. In this research, we either focus on just optimizing power consumption or just optimizing the exposure. So the value of the weights is 0 and 1 or vice versa. So the users are added consecutively, and the base station is then turned on, the base station that delivers the highest fitness value. So since all base stations are first turned on at maximal power, the base station will be turned on that is able to operate at the lowest power and then deliver the lowest exposure over the entire area. Then as the next user is added, it is looked at if this base station that is already active can serve the new user. If so, the user is connected to that base station. If not so, a new base station is activated, and then with the set of 2 base stations, it is investigated if the network can be optimized for the 2 users that are now being connected. Maybe at a later stage it becomes more optimal to reconnect users to a previous base station and so on. So this is reiterated until all users, for instance 224 users are connected. And in the end, once they are all connected, it is investigated if the EIRP, so the radiated power, can be decreased in order to reduce the exposure. That's of course in case if you optimize towards exposure and not only towards power consumption. So the results. So you can optimize either towards exposure. This is represented by the EG, or you can optimize towards power consumption, which is represented by the PC. Then you have 2 scenarios, the suburban and the rural scenario. And then you also have TV white spaces or LTE. So there are 8 combinations to be investigated. And Okay. What we first see, for instance, if we look at optimization goal low exposure, we see that the 45 base station locations that are possible, on average you will need 40 to have a network that is being that operates well and generates the lowest exposure. If you look at power consumption, on average you will not use the 45 base stations, but only 20 will need it for the 36 different user distributions, and on average only 15 will be used. So that's quite logical. If you want to reduce exposure, you want to turn on a large number of base stations, but with a lower power each. So you have a more homogeneous distribution of your field strength, a more homogeneous and lower field strength. So that's a bit the trade-off that you have to make. If you want a low cost, you will need fewer towers with a high radiated power. If you want a low exposure, you will need more towers with a low radiated power. If you look at power consumption, you see if you optimize towards exposure for TV white spaces, it's 3 kilowatts. If you optimize towards power consumption, it's only 1. So since you need more base stations, the power consumption is also higher. Similar observation, of course, for the cost. If you need more base stations, the cost is higher. If you compare LTE and TV white spaces, power consumption is all here 5 times higher and here 12 times higher in the depending on the optimization goal. And the same conclusions count for the rural scenario as for the suburban scenario. If we compare the two scenarios, suburban and rural scenario, you see that the power consumption on average will be lower since fewer base stations are needed because path loss is lower in a rural scenario. This I have discussed. So this was now looking at power consumption. If we now look at the resulting exposure, if we optimize towards a minimal exposure, you see here on the right, so Boyeros is rural and Ghent is suburban. I'll first discuss the lower part. If we compare TV white spaces and LTE, we see that exposure for TV white spaces is 65 to 70% lower than for LTE. So the 65 and 70% difference because of using TV white space. That's because of the better SNR and the lower noise figure, etc. That your radiated power can be lower, and in the end you have a lower exposure. If you compare the rural versus the suburban case, we see that for the suburban scenario also the exposure is around 70% lower than in the rural areas, and that's because the path loss is lower in rural areas, meaning that the exposure will be higher. If you again look at exposure, but now in the worst case, meaning that you optimize towards power consumption, where you want to have a small amount of base stations with a high EIRP in order to reduce the cost. We see the left column is the suburban area of Ghent, the right column is the rural area of Boyeros. And the upper two figures are for TV white spaces and the lower two figures are for LTE. So if you look at the suburban case, which is here, we have a maximal exposure of 20 millivolts per meter for TV white spaces when you are 200 meters from the base station. For LTE, this is slightly higher, 24 millivolts per meters. In the rural areas, we see that these high exposure values occur when you are even further away from the base station. So indeed, the exposure in the rural area is higher. This is also can be noticed by the red dots in the figures. So to conclude, we did a study on a comparison of LTE and TV white spaces with respect to exposure, power consumption, and cost in the network planning phase. We have seen that for LTE, power consumption is much higher, and also the infrastructure cost is higher. And also, we've seen in terms of exposure that the LTE exposure was around 3 times as high as for TV white spaces. Further research can be done to have a joint optimization of power consumption versus exposure, because now it was either power consumption or exposure. Of course, these are all advantages for TV white spaces, but LTE, of course, has its advantages as well. It's is more mature. It supports mobility much better, etc. So this is not just. I'm not just saying that TV white spaces is the best solution, but it's definitely a promising alternative for areas like Cuba, for instance, with a low population density. So Rodney Martinez Alonso is supported by Flemish grant, and he's partly working at Lassitel, Cuban research center, and partly at Ghent University. Thank you for your attention. I have a few minutes that I have left, so I'll try to answer some questions if there are any, and thank you for your attention.
Out in Cuba at all after the tests?
No, this is ongoing research now. We are also looking at IoT enabling receivers to dynamically adapt, for instance, the base station characteristics or transmit power. This is not being deployed yet. But since there's a close cooperation with Lassitel, it's a very good step up towards an eventual rollout, I think.